before you get to the delta math, I want to explain the why and the how to translate between the magnitude and direction form of vectors and the component form of vectors. So that, for instance, this right here, this 50 miles an hour, 30 degrees north of east, is actually equivalent to this component form 25 rad 3 I hat plus 25 j hat. Now, obviously, when we're translating between things, like sometimes it's going to be easier to say things and do things in one form. Sometimes it'll be easier to say things in the magnitude and direction form, and sometimes it'll be easier to do things in component form. And that's why we're doing this. So for instance, generally the magnitude and direction form is easier to understand and easy to measure. Okay? It's kind of harder to understand the component form and to measure the component form directly. However, what's beautiful about the component form is it's very, very easy to calculate. Very easy to calculate. And that's so generally what we're going to be doing in the real world, if you were using vectors, you would be starting with a magnitude and direction form because you would have measured it that way, and then you would have to translate it into component form to then calculate anything else that you want to do with vectors. So let's talk about how to do that. So let's say I've got a vector b, all right, that has a magnitude of 8, okay, and an angle of 60 degrees. All right? And we're going to turn that into the component forms. Now let's imagine that we've forgotten everything we know about vectors except for the core idea. And that core idea is that we can turn lines into right triangles. So I'm going to do that right now. I'm going to take this line. I'm going to turn it into a right triangle. Hey, it's got components and stuff. Wonderful. It has an x component and a y component. Wonderful. All right, so I'm going to in fact label those x and my y. But I also want to label, because it's a right triangle, I want to label the opposite, adjacent, hypotenuse stuff. So what is my x? Well, my x for this angle is the adjacent. And my y is the opposite. And the hypotenuse, which in this case wouldn't just be the vector, would actually be, the hypotenuse is going to be the magnitude. Okay? The hypotenuse, that's this one. So if I want to figure out what the x component is, well, how do I find the adjacent side? Well, I've got the adjacent, I've got the hypotenuse, so I'm going to have to, which one uses adjacent hypotenuse? Which trig ratio uses adjacent and hypotenuse? Well, it's cosine, all right? So if I'm looking to find the x, all right, I'm going to need cosine, because the cosine theta is equal to the x over the magnitude of the vector. Solving for x, I'm just going to multiply both sides by the magnitude of b, so that x is equal to the magnitude of b times cosine of the theta. Now, if I'm going to find y, I'm going to have to do something very similar. I've got the opposite and the hypotenuse, so my y, in this case, if I've got opposite and hypotenuse, if I've got the opposite and the hypotenuse, that's going to be sine. So if I'm trying to find my y, I'm going to use my sine theta. So sine theta is going to be equal to y, the y component, over the magnitude of b. Again, solving for y, I'm going to get y is the magnitude of b times sine theta. So plugging in the values here, and I'm just going to leave them as the green, it's going to be the 8 times the cosine of 60 degrees, and my y component is going to be 8 times the sine of 60 degrees. And we should all know what these are from the unit circle. So x equals 8 times 1/2 And the y is 8 times rad 3 over 2. So the x component in this case is going to be 4, and the y component in this case is 4 rad 3. So if I were writing this whole thing in component form, we're kind of out of space, but I would write it as 4I hat plus 4 rad 3 j hat. Let's do another one. So let's say we have component C here. And again, notice that you can think of these as formulas as well, where it's just the x component. The x component is always going to be the magnitude of whatever the vector is. Let's just call it v. All right, times the cosine of the angle. And then the y component is always going to be the magnitude of the vector times the sine of the angle. It's just always what it's going to be. So now, but if you forget these, you can just go back and solve for them again. It's fine. So plugging these in, I've got x equals 7 times cosine of 210, and y is 7 times sine of 210. So that in this case, x is 7 times negative rad 3 over 2, which would just be some sort of ugly fraction here of negative 7 over 2 rad 3. And then y is 7 times negative 1/2, which would make it negative 7 halves. Putting that in component form, I would have negative 7 halves rad 3 I hat plus negative 7 halves j hat. All right, moving on from components to magnitude. If I want to go from component form to magnitude form, we've already done this but in the previous video, but I just want to kind of review that. Let's say you've forgotten this. Well, you just draw the triangle, okay? So I've got 7, all right? I've got negative 4, sketch it out. I'm looking for this. Well, how would I find that? Oh, hey, I can use the Pythagorean theorem. So it's just going to be the magnitude of r is the square root of the 7 squared plus the negative 4 squared. So 7 squared, negative 4 squared. So the magnitude of r is just going to be 49 plus 16. So that makes the square root of 65. So that's the magnitude. So anytime you're doing the magnitude, you're going to use Pythagorean. So if it says, find, if you see something that's like find magnitude on the IB exam, it says something like find, OP or something like that, the magnitude of that, like that, it's just telling you use Pythagorean. So now let's go to something a little more complicated where we're going from component form to finding the theta. All right. And we're going to start with just Q1. But again, like if I don't know what to do, I draw the vector. So this has got an x component of 9 and a y component of 5. All right. I'm trying to find this angle theta here. Well, again, let's label some sides. So I've got a hypotenuse. I've got an opposite. I've got an adjacent. Hey, I know an opposite and an adjacent. Which trig function uses those? Hey, well, that's tangent. So the tangent of the theta is going to be equal to the opposite over the adjacent, so that's 5 over 9. And then to solve for my theta, okay, I'm going to have to use inverse tangent on both sides. So that your theta, when both components are positive, that's what this means, both components are positive, is just going to be tangent, inverse tangent, of the y component over the x component. And getting a calculator and plugging that in, it's going to be 29.0 degrees. let's look at, now that was for if it has both components are positive. Let's go ahead and look at what if at least one of the components is negative, less than 0, negative. All right, so in this case, we've got R, one of the components is negative. For Q, one of the components is negative. And for S, one of the both of the components are negative. So what are we going to do in this case? So what we would have to do is we are again going to use our inverse tangent. But it's sloped, so it's negative 4 over 7. And plugging that into the calculator gets us negative 29.7 degrees. However, that negative 29.7 isn't very useful. And if you notice, it would be over here in quadrant 4, 7 to negative 4. So what we're going to do to get it as if it were a positive angle, we're going to have to add 360 degrees. All right, so adding 360, and that gets us that the theta in this case is 330.3 degrees. Notice that Q would be in quadrant 2, and that if we were to set it up, to tan negative 1, it would be 4 over negative 7, which would actually get us the exact same thing. But it's in a different place, the same angle, same result from the calculator, but it's in a different place. It's in quadrant. So instead of adding 360, in this case, we're going to have to add 180. When we do that, we get 150 degrees for our theta. Now S is in Q3, so setting up the inverse tangent would be negative 4 over negative 7, which would make both of these positive, which would mean we would end up getting a positive 29.7 degrees. But this one, because it's in Q3, the reference angle, you'd have to add 180 degrees. So that would be 29.7 plus 180 this time, and that would get you 209.7 degrees. So notice, just to kind of summarize here, that if I'm in Q1 and I'm trying to find the theta from the components, that's the Q1's the easy one. That's the one where it's just the inverse tangent of the y over the x. I can use the components to make a slope, and then I can go from that slope to the tangent to get the angle. For the Q2 and the Q3, in case you didn't notice from that, I'm going to do the same thing, but what I'm going to do is I'm then going to add 180 degrees. Or pi if we're in radians. So that if my x is negative and my y is positive, or my x is negative and my y is negative, either way, I'm going to do the inverse tangent of the y components over the x components, and then add 180 degrees. For the Q4, that's when my x is positive and my y is negative. The inverse tangent is going to give me a negative, and so I need to add 360 degrees. So it'll be tan inverse tangent of y component over the x component plus 360 degrees, or 2 pi, to get a positive amount. So that's how you find the components, go from the components to the theta. If they're both positive, it's the basic one. If it's these other ones, you're going to have to use reference angles. Right now, you know everything you need to know about translating between the component form and the magnitude and direction form, and be able to go back and forth between those, which you should now be able to do everything on Delta Math. Have fun.